Good evening, everybody, and it's a pleasure to me to talk to people from Kansas and from Nebraska because, as Nicola already told you, I did my PhD. I did my postdoc in Lincoln, working on CMS pixels, and also in close collaboration with Alice Bean in Kansas. So it's a pleasure for me to share some time with you. So the Mu3e experiment. What is the Mu3e experiment? The Mu3e experiment is the search for this decay. It's a decay from a muon to 3 electrons in the final state. And this decay is extremely rare. Actually, in the standard model, it's suppressed by more than a factor of 10 to the minus 50. So the latest calculations are 10 to the minus 54. Why is it that low? So first of all, what is the characteristic of this decay? You have only muons in the initial state and only electrons in the final state. So this is a flavor changing channel. So in principle, this is to a large extent forbidden. The only decay you can construct, the only Feynman diagram you can draw in the standard model is this one here, where this muon here, this neutrino here, has to do neutrino oscillations to an electron before it recombines with the W to form the E+. Why do I draw here mu plus? Because we are creating mu pluses in our accelerator. So we work with anti-muons. So that's the reason why we have this. But this is our decay here. The current best limit, which you can still find in the PDG, is 10 to the minus 12. And it has been done also at PSI with the Syndrome collaboration in 1988. There were some attempts to redo these experiments, but no one did really beat that level here since 1988, which is quite a long time ago. So why is this the case? I will show you a little bit. So why is this interesting? Because there are a lot of alternative models. So it's Technicolor, it's fourth generation, it's also Mu3e that would open up the phase space to draw different diagrams here, which show an enhanced production. So that's the reason why we are interested, even though for reaching that level here, you will need a couple of universes to reach that and a huge detector. So we will never do that, I believe. So what is the muon itself, the standard decay of the muon? This is the thing that all the muon physicists call the Michel decay. This is this one here, you know it. It's the standard decay. 99.997% of all the muons decay this way. So you have the muon, you have a W, and then you have an electron, in this case a positron, the way how I draw it. And you have these two neutrinos, and a muon antineutrino and an electron neutrino. Everything is in balance. Nothing is no charged lepton flavor violation is in here. So this is perfectly allowed. And there is another observed decay, which is the decay that we call the rare standard model decay. It's already quite suppressed. It's at the 10 to the minus 5 level. This branching ratio has also been measured last time with Syndrome. It was the same collaboration, same experiment, 1988. But here, what you see in addition is that on this fermion line here, you observe that there is a gamma that gets radiated, and then from that you get an electron-positron pair. Keep this decay in mind, because this has more or less, for any reasonable detector that only can detect charged particles, this has the same signature, the 3 same tracks that we see. So how does our signal look like in the transverse view, R5 view in a detector? So it could be, so the same thing could also happen in CMS or in Atlas. It's just very difficult to detect. So it would look like this here. You have a positron, another positron, and an electron. So it's an easy signature. So it's easy to detect. And it's also a great signature because the sum of the momenta is 0. It's everything balanced. There's no hidden particle that goes out here. Then the invariant mass is the mass of the muon, very precisely known. So wonderful. And it's coincident in time. So all the 3 tracks are generated at the same time on that vertex down here. And we share a common vertex. So that makes it an ideal channel to measure. That rare decay that I told you already, this has the same signature. The neutrinos we don't see. Yeah? I don't even know where they go. So it depends on what model you take here. So I just, for illustration, I took this painting here. There, the sum of the momenta is unequal to 0, and the invariant mass is below the one of the muon. But still, we have a common vertex, and second, we do have it coincident in time. So, okay, this already tells you one of the key requirements of our experiment. We need to distinguish these two because this is a background to this here. We try to search it from on the 10 to the 12 to the 10 to the minus 16 level, and you have a background at 10 to the minus 5. So you really have to make sure that you can distinguish this from this, and we can. I will show you later. And then we have something really nasty. This is what we call the accidental background. This accidental background also looks very similar, but you see here there is a detached vertex, and I will tell you what this detached vertex comes from. So you can create that in our detector with Baba scattering. You know this Baba scattering Feynman diagram, because I think this is one of the mothers of all the Feynman diagrams when you do particle physics, when you do your calculations, the collision of an E plus and an E minus, and you can read it in the different ways. And in our case, we look at this at the fact on when we have an electron in matter that collides with an electron in motion, a positron in motion, exchanges the gamma and then knocks out this electron. So this is this electron here, the E minus, comes from our material, and the E plus is from another Michel decay. So the only ways to mitigate that is reduce material, because you need the E minus from somewhere. They don't come out of the vacuum, and we need to improve the resolution. Just to illustrate this a little bit more on how this works. So here we have the basic experimental setup of Mu3e. We have muons coming from a beam here from the left. They stop on a target. This target is a double cone, and inside it's hollow. So it's a tiny little cone. So the diameter here is 38 millimeter and the length is about 10 centimeters. And it's made of mylar, 80 micron mylar, and inside it's hollow. So now we have a muon that stops here. So we always, what we start with stopped muons on that target. And then this muon will eventually decay. So it's a standard muon. It decays into the standard model decay. Electron and 2 neutrinos. So, and then it flies maybe inside that cone to the other side of the cone. And then it hits an E minus, makes Baba scattering, and then you are left with an E minus and an E plus, a positron and an electron. And these two guys here, they form a perfect vertex because they can't originate in the target. So now, if there is something like Murphy's law, and I certainly know that this is true, then you will have a mu plus in its vicinity, stopping there and decaying to another E plus. And then you have our signature. That's a substantial background to us. And this we can only mitigate by having a great resolution and by minimizing material. And it's not only the target that plays a role, it's also some detector material, because we also have some muon stops in our detector, as I will show you later how the geometry actually looks like. So first, I give you an overview of the parts that are in the detector. Then we will delve into some technical details on how these detectors are made. I will focus then later on pixel because I'm a pixel guy. Then we will go again, then we will revisit again what is the geometry and what is the motivation for the geometry that we have chosen a little bit more. And yeah, that's more or less the roadmap for this seminar here. This is the Mu3e detector. This detector is connected to a beam line. So here, this is the transition area or section. So the muons come in from here. So that's where the muons get in. Then everything here is in a big magnet. I will also show you that magnet. It's a solenoidal field of 1 Tesla. And here, that's the center of that solenoidal field. So these muons, they fly in this way here. And let's unmantle that a little bit. So here you see our beam pipe. So we have an upstream beam pipe and we have a downstream beam pipe. And in between there is a target. That's this double cone hollow target. We have a beam window up here. So inside this is vacuum and the muons come out of here and then stop on this target. Around that, we have a lot of support. So in our case, it's cables, it's bus bars, because we have to provide a lot of current there to run the detector. And we have helium ducts. So I will tell you a little more why we need helium later on. And then we have around that the scintillating fiber detector. And the scintillating fiber detector, this is just formed of ribbons here. I will also tell a little bit more in detail here that are read out on both sides, and with that we get precision timing. And then we have pixel outer layers. There's also a pixel inside. I just forgot to have this as a single slide, but I will show you more on this. Then we have these pixel outer layers. So this is covered the whole barrel. So I only added a few modules here to indicate that what this looks like. And then we have scintillating tile detectors. These are little scintillators. I will also show you them later on, how this looks in detail, which are mounted on individual silicon PMs. And with that, we get precision timing for certain tracks. I will show you an event later on, a simulated event, how this would look like. And then we have recurve layers, which are more pixels up here and down here. So if you watch it from outside, all what you see is a long barrel. Huh? And to give you an idea of the dimensions, so from here to here along that, at 36 centimeters, and the whole length of this beast here is 1 meter, and the diameter is 20 centimeter roughly. So this is a very long detector, and the rest of the magnet is empty. The magnet diameter, the worm bore, is 1 meter. So, but there is reason for why this is empty, and later on you will understand that. So I will talk about several subsystems. I just make an opinionated selection here to give you an idea how this experiment is made of. So first, the magnet. All we need is a magnetic field, but how do we get a magnetic field? So we have a superconducting magnet that's made by a commercial company. Here you see the inlet, so the beam pipe would be connected here. The muons go in here, and then the experiment is inside this magnet here. This has a length of about 3 meters. The worm bore diameter, if you open these doors, so this looks like a giant safe when you open that. So we're in Switzerland, so we know about how safes have to be. And so then the inner bore is 1 meter diameter. And the nominal field of this magnet is 1 Tesla. It's a cryogenic magnet, and it's cooled with 4 cold heads up here. So these are the standard Gifford McMahon cold heads that you probably have in your physics department with some people who work at cryogenic temperatures, like some quantum people and things like that. This works very nice, actually. We have it. We received that magnet in July. It's 33 tons. And if you want to watch it, how it arrived, then just go to that link here. I can briefly show it. It's a pretty fast thing. It's 1 minute. So we received it here, the magnet on a lorry, and this lorry then got into the experimental hall. So some of you already have been at PSI, and then we craned that 33-ton beast with the large crane in the experimental hall and moved it over to the area where we preliminarily placed it, and then it landed. And yeah, that's where it still stands. and we are doing commissioning tests right now on this thing. So now I stop this. So later this year, we will perform the first beam characterizations with that magnet. The solenoidal field plays a crucial role in focusing the beam. So if you know a little bit about beam optics, solenoidal fields are very good in focusing while you're still in the solenoid. You cannot use it to focus a beam outside of the magnetic field. So the beamline itself, how does that look like? So here is the simplified view of our beamline that we have. So the protons come from here. So we have a proton accelerator, which has the highest intensity on Earth. So it has a beam current that we measure in milliamps. It's at 2 milliamps. That's how we have protons. So, but it's not at a very high energy. It's 580 MeV. So this is a low energy proton beam, so to speak. And we hit with that on a target. And on that target, we stop the proton, we create pions, and these pions eventually got stuck in the target. And at some point, the pion decays and produces a muon. And then this muon gets transported with these beam optics elements. So these are quadrupoles to focus it. Then we have some bending magnets and another set of quadrupoles. And then you see here, there's another experiment, the Mu3e gamma experiment, which makes a very similar search, just for another channel, a decay channel of the muon. It's for a muon into an electron and into a gamma, so in a photon. But with a clever beamline topology, we can switch that. All what we have added here is another bending magnet, and with that we get the beam into our experiment, which is located here. So then we have some detectors. So let me first talk about the scintillating detectors. The scintillating fiber detector barrel, it's a barrel, consists of these translucent ribbons. So these are ribbons made of fibers. The fibers itself, they have a diameter of 250 micron, and they're fabricated in 3 layers. So one ribbon has 3 layers of these fibers, and at each end, so here and here, you see these blackened sensors here. These are silicon PM arrays with 2 × 128 channels. So that's how we can read them out. And there is also, which is not visible here, it's down, it's on the inner side, there is an ASIC that makes makes then the timing with a timing resolution of 250 picoseconds. That's for such a compact detector which has been built with very low material, is this a very nice performance. So the material that has to be traversed by the positrons and the electrons is 0.2% of radiation length. So this is pretty low. That's the reason why we go for that. These are being fabricated now. So this is a station where we fabricate that. It's located in Geneva, at University of Geneva, actually, it's not CERN, where we have a spool with the fibers, and then we wind it around this this piece here, and then we fabricate these ribbons. And here you see a partially filled detector here with just a few ribbons so that you can still see the inside. Then we have the scintillating tile detector. The tile means that we have these little blocks here of silicon, of scintillator, plastic scintillator, wrapped in reflective foil. One of these tiles has a dimension of 6.5 by 6.5 by 5 cubic millimeters. So the 5 is the thickness, so this is this dimension here, and everything else is 6.5 millimeter. So these are nice little squares, and down there you see there are silicon PMs, which they are glued to, and this wrapped with reflective foil. And they have, of course, more material to traverse with the electrons, so therefore the time resolution is much better, so it's 36 picoseconds. There we don't care about the material budget, because this is already at the place where the electron track will die out. You will see that later again. So we're currently fabricating that, and 2 modules. So this is one module. 2 of these modules are currently being fabricated, and so far it looks nice. One little highlight is how we fabricate these little tiles. So what we do is we do a vertical milling here. So this is a piece of plastic scintillated, and we first mill this way here, and then we do it in the horizontal way, so this way here. And then we do the edges, because some edges are a little bit inclined. And we do that with a conical mill head, a custom one. And then we flip it and freeze it on a surface that you can freeze with Peltiers. And then it's frozen. And then you do the milling from the bottom, and then you also polish it. And then you have a 4x4 matrix out of 16 of these scintillators very nicely. So this is a pretty nifty method, and they've already produced plenty of these. And the optical properties are wonderful. So it's very good. Then now let me switch to the pixel detector, where I want to expand a bit more on how this looks like and what this is. So the pixel detector, what you see here on that screen, on that image on the top here is our pixel chips here. I will also explain a little bit more in detail how they are made. This is a very thin detector. So one chip here, including the HDI, so the high density interconnect that is down there, which is made of aluminum and capped on, this exposes only a bit more than 1 per mil of radiation length. So it's a really thin thing. So the chips itself, they are thinned down to 50 microns. I will tell you also why we can do that in a few minutes. But it's very, very, very thin. So it has the thickness of 2 sheets of paper. And then we have these flexes, which give an additional 2 sheets of paper. So it's like a little bit stiffer paper that whole detector. It's extremely lightweight. One of these chips here has a dimension of 20.23 square millimeters. The active area is 20.20. So hence also you see this overlap, so that shingle, it's a little bit like shingling. So they look out here, and this is the periphery place, the periphery area where we don't detect anything. The power consumption is very low, so it's below 250 milliwatts per square centimeter. The latest incarnation of that chip is now even better, but these are preliminary results, so we reach 200 milliwatts per square centimeter, but this needs to further confirmation, but we are very confident. The whole detector is instruments a bit more than 1 square meter. And it consists of vertex and record layers, and in total we have 2,844 chips. I will show you more about the geometry. What you see here is a so-called layer 2 module. We have 2 of them, so there will be a second one down here which forms then the full barrel, which closes that barrel, and it has 5 ladders here, and then on the bottom we have 5 ladders. So it's 10 ladders with 6 chips, so it's a 60 chip little pixel detector. So this pixel detector is a monolithic pixel detector. This means, in contrary to more traditional pixel detectors who have a sandwich out of a readout chip, a sensor, and bump bonded together, we have everything in one chip, in one substrate, which is a bit difficult to achieve, but then over the past few years, we managed to do that. What you do is you take a technology, a foundry technology that allows to create a deep N-well. So this is really deep. This is 20, 30, 40 microns deep. And then in that deep N-well, you place a P-well in it, and then you have all your CMOS electronics on top of that. So you have 2 more implants that you can do here. And with the P substrate that you have in here, you form then the diode, and the diode floats inside that substrate, and we connect that diode with standard techniques in CMOS electronics to the amplifier we have already in here. So this is a 3D view of the same thing. So here we have this PN junction. The charge gets created by the particle going through. Then you have the drift in here, and it's really drift that we do. Then we read it out. So we have an E field, and we also use a so-called high voltage technology from the automotive industry, so that we can bias it up to 8500, 100 volt. Down here, you see a test setup that we created last year. Here is an insert that just connects to our readout system. And then in between, we have a flex print, which is made of Kapton and aluminium. Hence also, so these silvery things are the conductors and the yellow thing is the Kapton or polyimide. And down here we have one of our chips, which is the Mu3e 8. Now we are at the Mu3e 10. This is the Mu3e 8 chip, and we could easily read it out over this long stretch here. It's 25 centimeters long over this very thin and aluminium flex print, or similar to an HDI. So the Mu3e itself, I call it because it's a neon pixel, is a highly successful line of monolithic pixel chips. It's highly efficient, so the efficiency is better than 99.8%. We have very low noise, so 1 pixel has a noise below 1 hertz per pixel. And this year we did some characterizations of the Mu3e 10, which we received this summer, and this results so far are wonderful. Currently there is a test beam running at PSI, so my colleagues, they have night shifts at the PSI now. And we are started the commissioning and manufacturing of the process, and the first module construction will happen this year. And in December, we have another beam time where we can measure this in a full configuration. So we will have a little subset of our detector that goes into the beam. Now let me do a little excursion here. Material effects to tracking. You know this formula. It's the Highland formula that tells you, that gives you an estimate on what is the expected deviation, the deflection angle when a particle traverses material. So let me illustrate that a bit. So you can find that in the PDG, and I'm sure you know that already. So when we go to LHC energy, so here is a momentum of an electron here, and this is this angle that you have. That you can calculate. On the left, it's in millirad. On the right, it's in degrees. And you can see 1 GeV electron deflects when it flies through 1% of material, of radiation length material, which is more or less what standard pixel have. They might have a bit less, they might have a bit more, depending on the brand you use, but then you have an angle of 1 millirad or 0.06 degrees. So this is pretty moderate. And if you go down to 1 per mil, so if you would take our detector in LHC, then the angles, deflection angles would be below 0.02 degrees. So it's extremely low. Eh? But now let's switch to the energies or the momentum we have at the Mu3e. So the maximum momentum of a positron we get there is 53 MeV. Then the plot looks, oh, what happened to that plot? Did we lose the curve? Yes, we did. We have to adjust the scale. Observe that change in scale. Here we had 2.5 millirads and 0.14 degrees. And here we have 100 millirad and 5.5 degrees. This is the regime we live in. So this is the maximum momentum we get in our experiment. And the minimum momentum, the cutoff in our experiment is somewhere between 10 and 15 MeV. So if we would go with a traditional hybrid pixel detector, we would have deflection angles in one layer between 4 degrees and a bit more than 1 degree. Tracking would be impossible. That's the motivation why we have to go to this extreme low material budget approach, where we go to about 1 per mil of radiation length. But still, then we have an angle of 1 degree. Let me illustrate this in another way. What you see here is a 50 MeV electron that goes through a simple toy tracker or a telescope, if you know what a pixel telescope looks like. And I do layers of detectors here. So I have 6 sensors, and I've spaced that with 50 millimeters. So the whole thing is 250 millimeters apart. Particle enters from the left. And now we go for a layer with a detector with 1% of radiation lengths each. So here we scatter 1%, then another 1%, another 1%, So this plot here is to scale, just to tell you. So this is 50 millimeters, and then you end up with a spread of 25 millimeters. And I just added the contributions of every single layer in quadrature. So the outermost is the likely envelope that the particles end up here with 25 millimeters after just 25 centimeters of path length. So this is pretty substantial. And when we go to 1 per mil of radiation length, then we end up with 6 millimeters. Still a challenge for tracking, but a lot better. So now what else can we do? We have a B field, 1 Tesla. So hence the tracks are helices. So how can we take this to our advantage? And one thing is this here. So think that this blue line here is the barrel of the detector. From the inside comes one of these positrons, flies around here and makes a hit here. And then of course it will experience some multiple scattering. So it could scatter to the right, then you have this gray curve here, or it could scatter to the left, and we had it here. If I superimpose these two, then you see more or less the envelope on where these particles could fly around. Well, this is it. But observe here after a half turn, the effect starts to cancel. So here when you do a half turn, then you get the best performance because the contribution of this last layer here to multiple scattering cancels. This is not a new idea. So every mass spectrometer uses this idea. So you have your beam of heavy ions, then you make a half turn in a magnet, and then you have your detector on this side, and then you ramp up or ramp down your magnet, and with that you get your mass spectrum, and that they precisely use it for that. They're not because they have multiple scattering, but they have a beam divergence, and this beam divergence is the same effect to a particle stream like multiple scattering. So this is an old idea, but we take it to our advantage. So we do optimize the radii of the detector, and we minimize the material per detector layer. So you already know it. We go for that Mu3e sensor. We take an approach in the mechanics, in the readout, in the cooling. So let's go to the detector geometry, because now we have the physical ingredients, what we want to achieve. You can now understand a bit better why we have this very thin, long geometry that I have shown you initially. So here we see a cross-section through our experiment. From the left, again, a beam of muons that stop here on that double cone, this hollow double cone target. And this is not to scale, so that I increased the vertical dimension here. Otherwise, it would be just a very thin thing. So this would be 1 meter and 20 centimeter just here. So I had to change that a little bit here. But then let's look at a hypothetical Mu3e decay. So here are the red ones are the 2 positrons, and the blue one is an electron. Let it decay in this direction. So the transverse view shows you here is here are the positrons, and here's the electron which goes in the other direction. So you then get hits here, 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 and here, and yeah, this starts to emerge why we want to do that, and why also this return, this half circle return matters in our case, because we are interested in first to measure in these 2 inner pixel layers. We want to extrapolate to the vertex. Then we do the timing in the scintillating fibers, which are here in the other view, and then we measure hits up here, so that we can propagate it through the vast empty space to where they hit again. But they can hit again here in the central part, or they can go up here, or they could even, as recurlers, go down here for maybe 10, 100 turns. So this is possible if it's very perpendicular out here. And this is pretty nice actually to watch, because it spirals down because it loses the energy in the material. It's a nightmare for reconstruction. So if you are in reconstruction of particles, then you don't like that. Okay, this is how it is. And this timing is very important for the timing coincidence. And then we then we have the ones that end up here in the tiles, where there is a massive beam pipe here. So the positron will likely stop here, and if not, then it will at latest stop here in the beam pipe. Same here, and this one here goes back to the scintillating fibers. So what are the performance ratio numbers we have or we require? So the beam that we have here is pretty intensive. So it's 10 to the 8 muon stops on target per second, and it's a quasi DC, direct current beam. So it's a constant beam that we have in here. Then the time resolution that we need in the pixels is better than 20 nanoseconds. We currently reach about 6 nanoseconds. And the vertex resolution we need is 200 microns on that target here. And the momentum resolution is about 0.5 MeV, which we achieve grace to that half circle approach that we use in here. A closer look to the central plot. So this is a zoom into this part here. So here we have this target. Again, we have these layers. I've shown you that sketch, that CAD model is from this second layer here. We have 6 chips, so this is 12 centimeters long. Down here you have a scale, and here you have a scale. And here we have it at an inner radius, another similar one that just have 8 facets instead of the 10 facets of layer 2. And then outside here, we have a number of facets here. So these are, we combine them in modules with 4 ladders. And here we have 6, so this gives 24 ladders, and this here gives 28 ladders. This is how this looks like. And then we amend that with more pixel layers. And of course, there are the scintillating tiles and fibers in here, but I excluded that from that sketch here. To give you a comparison on what are the radiation lengths of the pixel layers. So Atlas IBL, for example, has 1.2% of radiation lengths. CMS phase 1, roughly 1%. The ALISO upgrade, 0.3, and the STAR detector, already a decommissioned experiment that was in the US, reached 0.4. And the Bell 2 IBL that they have constructed in Japan is down to 0.2, and we want to reach 0.1. So that's what we want to do. The pixel sensor itself, I've already shown that here. I can go around that, but I want to show you the readout principle of this detector. What you see here is the pixels here, and here's the periphery. And if you are in the pixel business since a while, then you know there is a reason why so far the pixels have been in a hybrid design. The nice thing about the hybrid design is that you can optimize the sensor, the diode, in a custom process, and you take a CMOS readout chip in a standard industry CMOS process. This is what you get there. And the nice advantage of this is also that the electronics is separated from the diode, because you don't want to have any digital signals induced into your cell, because this would give fake hits. We don't want to have this. So we have this active pixel matrix. This means a lot of the electronics is in here. So we have the amplifier there. But what we don't have there is the digital electronics. The digital electronics, which creates these nasty pulses, is down here. Now I show you how a chip works. So in here, in such a pixel, we have the sensor itself, which is a diode, which is capacitively coupled to a charge-sensitive amplifier. Then this the signal goes to a source follower, which drives the transmission line that goes down here, and every pixel here has a transmission line. So in the pixel matrix, if you look with a microscope, then you see a bunch of transition lines. So for every pixel, there's an individual transmission line that ends up in the periphery in a mirror cell. And in that mirror cell, we have an amplifier. So it's another source follower. And then we capacitively couple it to a discriminator, where we can set the threshold with a tune DAC. And then also we can set a global threshold. So this tune DAC is only to adjust for the individual biases that these pixel cells have. And with that, we get the signal. So when we have a hit up here, we have the signal from that diode amplified by the charge-sensitive amplifier, and then we transmit it down here, and then with the discriminator we make a nice digital signal. This digital signal will be together with a clock. We will receive timing, and here we have a very fast clock, and then we create a timestamp, and then this data gets read out. And this here is is then the readout is at 2.25 at 1.25 gigabits per second. We have 3 such transceivers per chip, so we have a data rate of 3.75 gigabits per second. One hit, it's 40 bits in size with timestamp and the precise location. This is very impressive, and you didn't hear anything about a trigger in here. We don't have a trigger because muons, they decay at will whenever they want, and our material budget is so low we cannot afford any material to create a trigger. So everything is read out in our experiment. How do we cool that pixel? You know, I told you that we have 200 milliwatts per square centimeter of heat that get produced. So we do that by blowing helium at ambient temperatures and pressures. So this is 1 bar absolute pressure, and we start with 4 Celsius. So we blow in 4 Celsius helium, and then it comes out with about 50 Celsius, and with that we cool the chips. So here, these black lines here, these are the pixel chips, indicating here, because here we want to emphasize on these flows. In the transverse view, you see that we have this flow here. So this this bright red one here, this is for the pixel, for this the vertex pixel, which is inside the layer 1 and the 2. So in here we let that flow between these 2 layers. We did a simulation of that. So this is a view on this small detector, again with the 6 chip length. So it's 12 centimeters here. And we saw that we also create a vortex in there. This vortex comes because we have some, with these shingling, we have a preferred direction, and this creates it. And we made a prototype from little strips that we can heat. And we also saw that when we cool that with helium, we can confirm that vortex here. And we started to do some mitigation. So this is already 1 year old. The fun thing for this experiment, to tell you, we have to deliver 2 grams per second of helium. 2 grams per second is half a mole of helium. So this means this is 11 liters per second of helium. If you use a standard bottle, 200 bar, 50 liters, it runs for 12 minutes. You heard that right, 12 minutes. So within 12 minutes, we had to run this test, and then the bottle was empty. And if you know about the price tag of helium, it's 250 Swiss francs at the moment. This was quite an expensive test, just to run that for 12 minutes. How do we detect that? So I want to reiterate that and recapitulate that as a conclusion. So we have this decay. The first hits we get are down here, and in the transverse view we see here, these are these little stars, yellow stars. And then we have the next ones, it goes out here. Then we get the timing information from the fibers. Then it goes out here to the recoil stations, the recoil layers, and then the next one. And then we have to wait until they eventually return wherever they are, here, here, or here. And then we get the hits there and another hit here. And then in the end, we get the signal here in the tiles. And eventually, if it hits it, we also get it from the scintillating fibers. This is, again, what is the physics we're going to do. How sensitive are we? So this is a plot from simulation. On the left, we simulated 10 to the 15 muon stops at a rate of 10 to the 8 muons per second. So you can calculate, this is 10 to the 7 seconds. So this is what we can achieve in maybe 1 year of running or so with some certain dead time. And then we have the different types of signals. So here, this is that background from the rare decay here, Mu3e electrons and 2 neutrons. That's how this looks like. And then we have a few rare events of Baba. And if Mu3e exists at the level 10 to the minus 12, 13, 14, 15, so it's the same curve, it's just shifted, then the signals would look like this here. So if it's at 10 to the 14, something that the previous experiment definitely couldn't see, then our experiment, our plot that we would publish would look like this here, and then this shoulder here would be the Mu3e. So we'll see if this happens. In a 2D phase space, so here's the reconstructed mass, the invariant mass of the muon, and here is the momentum in the CMS. Then you would see the signal here with this shape here, and then you have in this plot here in red the rare decay, and in blue it's the BABA. Please observe before you judge. There is a change here in the, so the 3 orders of magnitude difference between the Michel-Baba background and the radiative or the rare background. The reason is this here is much easier to simulate than this here, because here you always have to run full propagation in the detector into the material before you can then again decay it. But this here you run your generator and then you propagate it to through the track, and it's much easier. This here runs a day to simulate, and this here on a cluster runs for months. So, and to increase that by a factor of, by 3 orders of magnitude, yeah, you wouldn't see the plot yet. What's the sensitivity then in the end? So this is on the abscissa, we have the data taking days, and here is the branching ratio sensitivity. So here we have the 95 confidence limit, the 90 confidence limit, and the single event sensitivity. And here is the limit to 2 times 10 to the minus 15, which is what we can reach in the first phase, the first running of a couple of years of our experiment. And then you can see that we can reach single event sensitivity at this level after about a year of data taking, continuous data taking. This is not what we can do because there are interruptions, but on the 90 or 95% level, we can do that much faster. Beyond phase 1, I already mentioned we have a phase 1, and so this implies we have a phase 2. There we have to extract the muons in a different way. So this is currently a feasibility study going on. So this is not 19. This is, sorry, this is 20 times higher muon rate. So we want to increase the muon rate here by 2 orders of magnitude. So it's 100 times actually. I probably wanted to type something 10 to the something, and it didn't work out in LaTeX. But we have a new target design, and then we extract with solenoids. This is a feasibility study, and with that we would increase the muon rate on the target by a factor of 100, and this allows us to reach a much higher sensitivity. This is the high intensity muon beam project that is now started at PSI. So let me conclude. Mu3e is a challenging venture, as I hopefully explained to you. It uses new technologies that makes it possible: ultra-thin pixel tracker for low material per layer, a gaseous helium cooling. We use cutting-edge and highly compact scintillator-based detectors for precise timing, and we have a fully triggerless system, so everything done is on a filter farm, so which is just our dedicated cluster. The TDR, the Technical Design Report, has just released 10 days ago. You can find it here on that link. This is the archive link. And then you can also find our project website, which is hosted at PSI. Yeah, that's it. And what is our collaboration? Here you see a subset of our collaboration in a collaboration meeting last year. This year we couldn't have one for obvious reasons. But you see it's a collaboration in Switzerland. CH stands for Confederatio Helvetica, so the Latin word for Swiss Confederation. It's from University of Geneva, it's ETH Zurich, and it's University of Zurich. From Germany, it's University of Heidelberg, Karlsruhe, in Karlsruhe, of course, and then University of Mainz, and then we also have people from the UK, which come from Bristol, from Liverpool, from Oxford, and from London, and of course, the host lab at PSI. So thank you very much for your attention, and I'm open to questions.
So thanks a lot, Frank. This was really interesting. You had to condense a lot of stuff in a relatively short seminar. Thanks for that.
You're welcome.
We give you a virtual round of applause. Of course, you have to live with that. We cannot do better.
I know, I can imagine.
So I start with a kind of personal curiosity, because I work on timing detector mostly, and on slide 19 you showed that the tile detector has 35 picoseconds.
Yep.
Now I'm interested in this because it's an extremely good time resolution.
Yep.
But I'm wondering if this is the full detector, well, 36, yes. The full detector or only the CPM with the electronics?
No, this is this has been tested in test beam. So it's 36 picoseconds when we had such a module in the test beam. There was a telescope in front of it and a reference scintillator to get the timing. and this is this tile here and the silicon PM. So it's a pretty good scintillator with high light yield. So we have several hundred photons that we can measure, and this is individually measured on the silicon PM. So for details on this detector, I refer to the TTR. There you can find which scintillators we are using and which silicon PMs.
Nice, nice. Because usually all the scintillators that I've used are way lower than this. So yes, of course I will have a look. So are there any questions from the audience? You can raise your hand or you can unmute directly yourself. Yes, we have a question from Philip.
I was wondering, for this level of sensitivity, do you have to worry about muon interactions with nuclei in the material?
Not really. It's already pretty thin, and we avoid any heavy nuclei. So it's more or less carbon, hydrogen, and silicon that we have in there. So of course there are occasional such interactions, and we would just see then the muon or the positron if it decays in flight, which we would neglect in our filtering.
Okay.
So it's not a competitor to Mu3e.
Mm-hmm.
No.
So next question. While I see that everybody is shy, I actually have another question.
Yes, please.
So also Alice in the upgrade is going to use the maps for the tracker, and they
Yes.
are also 50 microns.
Yes.
Are they the same? They are different. What is the difference if they are different?
Okay, as you know, in heavy ion experiments, you have a different pattern of the hits. So there, normally you have for a long time you don't have a collision until you get one, and then you have a firework in your detector. So therefore, they're not so much interesting in having this precise timing. So they have a lot of time to read it out. So their Alpide detector is a very nice one, but is optimized for the case of heavy ions, where you then, when you have an event, then you can read out and you have your time to read that out. Our detector would be useless in a setup for heavy ion, because you would immediately overload all our connections. So because then you have maybe in one chip you have 100 hits in one instant, and that's our topology cannot handle that. So, and they also have a different solution for cooling. So that's why they end up with about 2 per mil of radiation length compared to us. But they need a more robust structure anyway than we do. We have a very bad resolution because a very bad intrinsic resolution because of our low momenta that we have. So we can afford a little bit of uncertainty from the position if anything vibrates or moves, which is not the case with LEs. They need the ultimate position precision. Otherwise, they got lost with the multiplicity of tracks they have.
Thanks a lot. That's nice. Well, I guess also they have more layers all compact together.
Yeah, it's a totally different design, which is optimized for their use case. Ours is optimized for our use case. So you could also not use it in an LHC experiment, for example, because it's non-triggered. You also read out every noise pixel. It's low, but it exists.
Okay, and finally, you said that there is no trigger. There is no hardware added for the trigger. Exactly. But do you read everything and you have kind of an high-level trigger? You have some kind of new technology also there, like you use FPGA to accelerate or GPUs?
Yeah. So I was not focusing on that. Otherwise, I would have overrun heavily. But what we do, we read out everything, and then it goes to a filter farm that first consists of FPGAs, which do a lot of the event building. So the event building is done in the FPGAs, and then it gets transferred to GPUs where we do the tracking. So all the tracking is done on a farm of GPUs, which are then in connection with the CPUs, which manage these GPUs. And with that, then we get the events, and the CPUs then decide to keep an event or to throw it away. The event rate is high, so 10 to the 8 hits of 10 to the 8 decays per second. So when we have 6 to 8 hit information that we have to digest, sometimes when we have a recorder, it's even more, but say 8. So then it's 8 times 10 to the 8. So it's about 10 to the 9 hits that we have to digest with a hit size of 40 bits. So then we end up with 10 to the 10 or order of 10 to the 10 of the data rate that we get per second, which is 10 gigabits per second, and that we read it out constantly, and that gets reconstructed. There is also some overhead, so it's more than these 10 gigabits per second. And we can only afford storage of this full data rate for a few seconds. Sometimes we are going to do that because for calibration we need everything. So it's something like the random trigger that you have, and we need it for the same normalization purposes. But then we run the filter farm, which reduces the rate by a factor of 100. And this is affordable nowadays for storage.
Thanks, that's very nice. I mean, like I was saying at the introduction, this is really, for the LHC, they are starting to do this. CMS is planning to use GPU, but for the high-level trigger, not for the first-level trigger. And the LHCb will go maybe triggerless for the Lumia plate. But we are talking many years from now. So it's
No, we have it, and we already demonstrated it that it works. So with a small subset of detectors, we played around and we had it run in test beam, and it was wonderful. The nice thing there is you get your real-time histograms of your tracks. That's really cool. So root is slower than the full DAQ for the plots.
Well, I can imagine.
It's marvelous, I can tell you. It's something. If we have telescopes where our telescope software, we make telescopes out of our own pixel chips and use them to characterize our pixel chips. And we have FPGAs and GPUs running, and this gives you a totally new test beam experience because you have it online. It's really cool.
So Frank, when is this? So when is your experiment supposed to start taking data?
So we currently we have to rework our schedule due to the COVID crisis, but our intention is still to commission our detector in 1.5 years. So we still have a chance to reach that, and then data taking will not start before 2 years because commissioning will take some time until we have everything running and everything is under control. We have also possibilities of a staged approach, so that we first start with just these inner parts. Where do we have this? Here. So where we can just install this one here, so to reduce the channels by a factor of 3, and then we can start with something like this here. So first data takings of the first test with a subset of detectors in the real experimental setup will take place this December. And we are currently preparing this, and everything is in full swing. So we hope we can travel. So currently we are allowed. So people from Germany and from the UK can travel. UK is a bit more difficult than Germany.
So we thank again Frank with another virtual applause, and good evening to people in Europe, and well, good late afternoon to people in US.
Yeah, you're welcome.
Bye-bye.
Goodbye.